In this section, we're going to look at conditional probability and an important rule in probability called the multiplication rule. The first rule is the conditional probability. And in a conditional probability, we assume an event has already occurred, and we determine what the new probability would be, assuming that another event has already occurred. So the notation that we use is probability B assuming A or given A. So we read this as the probability of B assuming A has occurred or given that A has occurred. Let's take a look at an example to help us understand how the conditional probability works. If we have two cards and they are selected in sequence from a standard deck, meaning one was drawn and then another was drawn, find the probability that the second card is a queen, given that the first card that we drew was a king. And we're assuming that the card was not put back into the deck, right? So it's not replaced. The way we write this, or the way we can write it, is a probability. Originally what we're looking for is the queen here, right? So we're trying to find the probability of the second card being a queen. And all we're finding here is the probability of the second draw. We find the probability that we're going to pick a king, assuming that we picked a king on the previous draw. The reason why it's important for us to put this part in here is because the drawing and non-replacement of the king card is actually going to change the probability of the queen. Normally there are 52 cards in a deck, but we've already taken out one king, and so that leaves us 51 cards left in the deck, 4 of which are queens. So the conditional probability here affected the sample space in this particular case. It only affected that in this particular case because we assume we pick a king, and so there's still the same number of queens as there was before. Now, if we were to do something like the probability of picking a queen, assuming that we picked a queen on the previous draw, so not a king but a queen, still the same difference in our sample space. There's only 51 cards still left in the deck, but now there's only 3 queens left because we assumed that the first card we picked was a queen. So it's important to pay attention to, because sometimes both the numerator and the denominator change, as in the second example, but sometimes only the denominator changes, just depending on what was removed from the deck previously. Let's take another look at an example where we have a table showing results from a poll. In this case, we divided up the sample that we took by male and female, and then we asked, have you ever been offended by something on social media? Some people said yes, some people said no, so we have our totals here. Now, let's get to the question. Find the probability that the user is male, given that the user was offended by something on social media. So let's write that out. The probability we're looking for is what we write first, the probability that it's a male, right? And then we want to look at the given. And here it's nice for us, they use the word given. Let's say given that the user was offended. So let's say that they said yes to the question, they were offended on social media. So probability it's a male given that they said yes to that problem. So assuming they said yes, this means that we already know that whoever we're finding the probability, we want to find the probability that they're male, but it's already given that they said yes. Since it's given that they said yes, this is the only group that I'm going to focus on. Because if it's already given that it's yes, there's no point in me taking the entire total, right? Because if it's given that they said yes, then this is really the total that we're selecting from. we can just assume that it was a no, or that none of the no's were even had a chance of being selected, right? So another way to word this is we're saying, of the people who said yes, what's the probability that they were male, right? Of the people who are of always means, hey, here's the group that it's out of, right? So that's another way of saying given. So again, just like before, this conditional probability changes my sample space. We're only going to take into consideration the people who said yes, and then we want to say, all right, of those people, how many were male? And the answer is 532. As a rule as well, we're going to round this to about 4 decimal places. So for reporting it, we want to get pretty specific, and we'll take it out to 4 decimal places. In this case, 0.4622 or 46.22%. When we have sequential events, one following another, we have 2 different types of scenarios that we come across. One is that we have independent events, and if 2 events are independent, the first one occurring does not affect the probability of the other one occurring. So if one occurs, it doesn't change the probability for the next one. In that case, the probability of B, assuming A occurred, would equal just the probability of B, right? Or if this was reversed, if we're finding the probability of A and we're assuming B occurred, but if the events are independent and one doesn't affect the other, then the assuming or the given of B occurring or the assuming of A occurring doesn't change the next probability, then we say the events are independent. But if they are not independent, then we're saying they're dependent. The last 2 events that we looked at, the occurrence of one did change the probability for the next. The first event was a card being drawn, right, a king, and so that changed the probability of the next event. Also, assuming that someone had been offended by something they saw on social media, assuming that to be true, probability of male changed. Because if we were just saying, well, what's the probability we randomly select a male, we'd take the total of males out of the total population, including females. Okay, so question 1, selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen from the deck. That's what we saw in the first one. So these are dependent events. What about tossing a coin and getting a head, and then rolling a 6-sided die and obtaining a 6? This is event A and this is event B. We say, does the occurrence of getting a head affect the probability that when I roll a die that I would get a 6? We can say these 2 do not interact or interfere with each other at all. These would be independent events. In fact, we could have just flipped the coin if it was the flipping a coin twice in a row or rolling a dice twice in a row. Still, the probabilities wouldn't change for those individual rolls. The first roll is independent, completely independent of the second roll. The first roll or the first toss doesn't affect the second event at all. What about driving over 85 miles an hour, event A, and then B, getting into a car accident? Well, most likely, if the first is occurring, then the second would be affected by that, right? If we're speeding, we're probably going to put ourselves in greater danger of getting in a car accident and also increasing the likelihood of getting seriously injured. So these 2 events would be dependent events. Most events are dependent, especially when we look at sort of real world things aside from tossing coins and rolling dice. Even pulling cards from a deck is somewhat of an artificial type thing, right? It's just a trial that we've set up with a standard deck of cards. But had we replaced the queen or the king before we made the second draw, that would make them independent. So sometimes it's the rules we set up as we are carrying out these trials. This brings us to our next important rule in probability, the multiplication rule. The multiplication rule always applies whenever we have sequential events, one following another. So the probability that two events A and B will occur in sequence is the probability of A and B. In fact, we can think of this as A and, I like to think of it as A and then B occurring. So A occurs first, we write out that probability, and then we multiply it by the conditional probability, assuming these are dependent, the probability of B given A. Since independent events don't affect each other, when it's independent, the second event is really just probability of B, right? Because the probability of B is going to be equal to the probability of B assuming A occurred, because if they're independent, the occurrence of A isn't affecting B at all. But this is kind of our general rule here, mostly because most events are dependent, but also if they are independent, taking into consideration the occurrence of A and how it might affect B is important for our thought process. We always want to think, does the occurrence of the first affect the probability of the next? Let's go ahead and revisit our first problem now that we looked at the multiplication rule. Same scenario. All we found previously was just the probability of the second event, but what about the overall probability of the entire situation? Two cards are selected without replacement. And from a standard deck of 52 cards, we want to find the probability of selecting a king and then selecting a queen. It's important to note that we have 52 playing cards in the deck. We're not counting the jokers, right? Without the jokers, there's always 52 cards. So let's express this correctly. We want to find the probability that we have king and then a queen. Right? The order is important. It would be a different probability, even if it had the same number attached to it, but it would be just a different scenario, picking the queen first, followed by the king. So it's important the order we put these in. We're going to find the first probability, the probability it's a king, and then find the probability of picking a queen, assuming or given that a king was already selected. The first is 4 out of 52. There are 4 kings in the deck of cards. And once we have selected a king, there are now 51 cards in the deck. There's still 4 queens because we're assuming a king was removed from the deck, which still leaves us with 4 of every other suit in our deck. The product of these two gives us 0.0060, which is 0.60%. So less than 1% chance that selecting 2 cards, I would get a king first, followed by a queen. If order was not important, this would be a whole different scenario. But in this case, we're looking for a very specific sequence where this occurs first and the queen occurs second. On the previous problem, we had 2 dependent events because the removal of a king from the deck changed the probability for picking a queen on the second. Instead of the queen being a 4 out of 52, just like the king, it was 4 out of 51. That's a slight change in the probability. Here, if we're tossing a coin and then rolling a die, 2 things. The first thing is rolling a die. We want to toss a head. And then second, we're going to roll a 6. Now, this scenario happens to be independent events because the coin toss and the resulting probability of that is not going to affect what I get on the die when I roll it. So the first one, the probability of getting a head, well, that's 1 out of 2. And of course, the probability of getting a 6, assuming a head was rolled or tossed on the first, would be the same regardless of the outcome of that coin, 1/6. So you can see here that the probability of 6 given heads is the same as what I would put if I was just considering the probability of 6. In fact, these two are equal to each other because the events are independent. This becomes the decision criteria for deciding whether two events are independent. If the probability of A assuming B is equal to the probability of A, then we say the events are independent. In other words, if the occurrence of the first event, in this case B, occurred first, we're trying to find the probability of A, assuming B already occurred, and it was equal to just A by itself, that means the occurrence or the first event B didn't have any kind of impact on A. For another example, for anterior cruciate ligament, ACL, reconstructive surgery, the probability that the surgery is successful is 95%. The question then is, find the probability that 3 ACL surgeries are successful. So what we're just going to say, I'm going to use the word success, or S, followed by another success, then followed by another success. Hopefully it's not on the same person. But the probability that we would have 3 successful ACL surgeries in a row is going to be probability of S followed by S followed by S, right? So again, sequential in a row. And we're assuming each time that the previous one was successful. Question is, does that affect the next one? For the third, we're saying that the past 2 were successful. So success followed by success. Well, each independent surgery, unless, one is making the doctor more tired, we could assume it really doesn't affect the next one, right? These would be considered independent events. And so really this is 0.95 times itself 3 times, or 0.95 to the third power. 0.95 to the third power is 0.857. And then we'll put 4 there. So this is approximately 85.74%. So almost an 86% chance that we would have 3 successful outcomes in a row. For anterior cruciate ligament reconstructive surgery, probability is successful is 95%. Find the probability that none of the 3 ACL surgeries are successful. Okay, well, if there's a 95% chance of success, so the probability of success for one event is 95%, we can say the probability of its complement, so here we're using our complement rule, S prime, which is the same as failure, would be 0.05. So we can either write, you don't have to put S prime, but we could put failure, followed by a failure, followed by a failure. A shorter way to write this, where we assume you are saying and, is just FFF. FFF means we have this first, this second, and then this third. And we're assuming it's an and there. We're just shortening it up. So again, this would be 0.05, 0.05, and 0.05. There's this 3 very specific outcomes that we're looking for, and is that the first, second, and third are sequentially not successful. So 0.05 to the third power gives me, on your calculator, you should see 1.25 E minus 4. Well, this E minus 4 actually means, the negative means move your decimal to the left, and this is the number of spots 4. So doing that, 1, 2, 3, 4 gives us 1, 2, 3 zeros, and then my 125, so 0.000125. This would be 1/10,000th of a probability that I would have those in a row. So very, very unlikely. If you put this into percentage terms, it would be 0.0125%. So very much less than a 1% chance of this occurring. So sticking with the same scenario, I want to point out that for the first one, we were finding the probability of 3 successes in a row. For the second one, we were finding the probability of 3 failures in a row. So very specific outcomes, all successes, all failures. In fact, we can take a look at this from the standpoint of a tree diagram. Either this would be the first patient, right? Either it's a success or it's a failure, right? And then for the second surgery, we would branch off of this and say, well, it's either a success or failure. If the first one's a failure, then the next one can also be a success or failure. And then the third would be an S and an F. Again, S and an F, S and an F, S and an F. So one thing I want you to notice here is that when what we found is this branch here and this branch here. But there's 8 other things that could occur. I could have the first 2 be successes and the last one be a failure. I could have the first one be a success and then the next one be a failure, the next one a success, or maybe we follow it with 2 failures. So there's lots of different pathways here. In fact, there's 8 different ways, 8 different outcomes. We've just found 2 of them. For this problem, what they're asking us is to find that the probability at least one of the 3 surgeries is successful. At least one. Now, it's tempting to just go, okay, well, let's just say, for example, that the first one was a success, the next 2 are failures. That's great. That would fit, right? At least one. Here, the first one is, and then the second's a failure, third one's a failure, but at least one of them was a success. Also, it includes all successes. If we have all 3 successes, that's at least one, right? There weren't any failures, so we had at least one success. In fact, we had 3 in a row. When we say at least one, we're finding the probability if X is the number of successes that X is greater than or equal to 1. Now, looking through here, we want to put a check mark next to every possible path that would define this that would define at least one. So all 3 successes, 2 successes and a failure. The next one, yep. Success, failure, then a success, yep. Then we have success, failure, failure. Well, yeah, that, again, as we saw, was at least one. In fact, looking through this, failure, success, success, yeah. Failure, 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 success, failure, yep. Failure, failure, success, yep, at least one. All of these have at least one success in them. Some of them have 3, or, the one column over here. Some of them have 2, and some of them have 1. So in other words, if I were to list out all the ones that qualify here, we would have the probability of all 3 successes, plus we could also have 2 successes followed by a failure. And then the failure could also happen on the second one, so success, failure, success. And then we could also have the first one be a failure and the next 2 successes. Or I could just have 1 success followed by 2 failures. And then that S can make its way through each position, failure, success, failure, or failure, failure, success. Right. There's 7 different ways that we could successfully have at least one. Each of these is unique. It's a unique outcome. If you don't think it's unique, tell that to the first 2 who were failures and then the last one who was a success. What if you were the first one? Is that different than the first one being a success and the next 2 being failures? Absolutely. Different scenario. they actually would have the same probability, but different scenario. Here's where we can use the complement rule for finding this. If we were to add up all 7 of these probability columns and find all 7 of them, add them up to get our probability, it's going to be equal to 1 minus this. In fact, if we added up all the paths, we would have 100%, right? These are all the scenarios. But there's only one scenario missing. So here, when I find the probability of at least 1, and I'm just going to go ahead and write that. Probability of at least 1 success. We see that it will be equal to 1 minus the probability of all failures, so no successes. This is a formula you can take to the bank. Whenever they ask us for at least 1, it's always going to be the complement, or 1 minus the probability of all failures. And that is a much easier way to find this. I'm going to erase all these because I don't want to find all those paths and add them up. I just want to find the complement of probability, if x is the number of successes that is greater than or equal to 1, is going to equal 1 minus the probability of failure. So that would be 0.05 times 0.05 times 0.05. And so the probability we're going to have at least 1 success is 1 minus 0.000125, which we saw on the last one. So that gives me 0.999875, or 99.99%. There's a 99.99% that we will have at least 1 successful outcome out of 3 surgeries. Now, I don't know if that makes you feel better, but there you have it.